So I'm Sander. I'm from Belgium. I do research on molecular simulation in a broad sense. So I'm not really tied to any particular application from material science or chemistry, but we do general method development here. And so I guess today's about the framework I've tried to build using Parsl, and also about my experience as a developer to let's say, get users who are completely unacquainted with Parsl to use a framework that is built on Parsl. So quick recap on the sort of the type of tasks that are involved here. So molecular simulation, it's typically a combination of two big tasks. So out of the four steps that you see here, you start from some atomic structure, and then there is a kind of interaction potential that describes the physical interactions between the atoms. That potential can be used to sample some probability distribution, and finally, that gives you physical properties. And that's basically how most of the molecular simulation workflows look like. The computationally non-trivial stuff is in the interaction energy first, because that involves quantum mechanical calculations. That's like mostly done on CPU, multi-node, high memory nodes, that type of thing. And then the second part is the sampling. That's more modern, let's say. That's mostly done on GPUs with state-of-the-art models. But this can be done in a massively parallel fashion. So there would be maybe 1,000 simulations running all at the same time, and you want to exchange some information between those simulations. Those models need to be trained on data. So all of that is sort of involved there. So it's very heterogeneous in terms of the hardware requirements, and also at any given moment, it might need a combination or only CPU or only GPU. So it's intrinsically load imbalanced, let's say. So the goal was to build a library for molecular simulation based on Parsl. It should be easy to set up for Slurm, and it should have a very strict separation between whatever scientific workflow you're actually trying to execute, and then all of the execution side details. And Parsl already does this with the config.load, parsl.load. But I think for, let's say, non-technical users, that was not enough. So in terms of API, we decided to basically hide as much of the features and apps from the user as possible. So the library consists of just basic classes which wrap around the essential concepts of Parsl. So in this particular case, none of this is actually a feature, except at the very end. The final output of the workflow would be a feature, which the user would have to call result on to get an actual value or to write that actual value to a file. But everything else is completely wrapped. And the reason this is done is because, so this is basically what a basic class in psiflow would look like. So it's the attributes of the class. Those would be then features or apps or whatever. Be more closely tied to Parsl. But the interface that is exposed to the user kind of does all of the app calling in the background. The reason being is that calling an app sometimes involves creating a list of inputs, or maybe finding the right executor to call the app, something like that. And all of that logic we kind of want to hide from the user. Even more so because the type of tasks, there's only a limited number of type of calculations involved in psiflow. You have molecular simulation, you have your quantum mechanical calculation, and then everything basically builds on those kind of tasks. So there is no need to support, arbitrary functions or something, because it's application specific. It allows us to narrow it down and to hide a lot of the flexibility that Parsl offers us from the user. So basically the way it's executed is the Python file defines the workflow, but nothing else. And a YAML file defines all of the execution stuff and nothing else. The YAML file is structured similar to, let's say, the Parsl paradigm. So each main entry in the YAML corresponds more or less to an executor. And so it has a few options. And one of those options is, of course, the resource provider. In this case, for model evaluation, there's a resource provider for Slurm. And all of the options you give into Slurm are just forwarded into the corresponding Parsl constructor. So it's by default so it leans very closely to the Parsl API, so there's no need to duplicate a lot of code or something. But what this does do is it kind of I've experienced that when I'm explaining this to users, that they find it a YAML file a convenient file format because it's very condensed, a lot of information in a small amount of space. And for some reason, it appeared to work better than if we wrote this in Python code. But essentially, all of the options in Parsl, so either directly on the configuration or options for the executor or options for the provider, and even, let's say, launcher-based options can basically be set via the YAML. And yeah, this was done in order to basically reduce the barrier. Some let's say issues I encountered, which I would have wished I knew a solution to faster than well, me having to figure it out for quite some time. The first one was that some apps, sometimes if they run out of memory, they tend to just kill the entire worker process. And this is something that's just annoying. This, to overcome this, I used ulimit settings. So just, if anyone is encountering this type of thing, yeah, this might be necessary because then the out of memory, of course, still occurs, but it's more graceful and it doesn't kill the entire worker process. Yeah, at some point I ran into throughput issues. So the more logic you hide from the user, also the more administrative tasks you're going to get and the more, let's say, overhead there's going to be. I found that it's yeah, the best thing is obviously to use thread pool as much as you can and work you only for tasks that take like minutes to hours to days. But that's, yeah, fairly obvious, I guess. Yeah, so as I've said before, so the by far the biggest hurdle was still that I've tried to build a library for a community that's not very computational, and I am also not very computational. And yeah, I think the most useful things that I've found in this aspect was to hide much of the technical app thing. Just make sure people are up to date with what a future is and what it means for a future to, well, to wait for a future. But that's about it. And use a separate file for the execution configuration. And then one other thing that was greatly helpful was to containerize everything. There are technically two ways to do this. So you can either run your entire worker inside a container, which works because they have access to the same network as the hosts, at least if you allow it to, but on most HPCs, or well, on the HPCs that I have access to, this is no issue. You can also choose to run the worker, using the host installation of CC tools, but then just have the user supply a very long launch command, in which case the launch command is not just the binary, but it's just wrapped in the container. This gives more flexibility. It also avoids the need to have Parsl and whatever other dependency installed in your container. But I found the two cases to be useful in different scenarios. So psiflow actually uses both. Right. So the biggest hurdle was getting users to understand that when blocks are requested, that doesn't mean that, that blocks can continuously execute tasks, that these things are decoupled from each other. And maybe finally a note on debugging. So I've often had users then, ask me, okay, the stuff doesn't run and I don't know where to look for the error. And this is probably a common complaint you've had from other users. I think there are just 4 locations where you need to look. And these 4 are also, I think, the order in which I would look at them. So first, obviously, the main job, or let's say the main process is output. Second one, Parsl log. Third one, any bash output logs. And fourth, if there's nothing there, then probably the block didn't start or it got killed or whatever, and you would find some information on that in the submit scripts directory. But so I've also included this now in the FAQ. Let's say these steps, and I think that's also important. Then something I'm working on, which might be relevant to you. So in a lot of cases, it was difficult to get people to, let's say, understand that when you have to configure the Slurm provider, that it's really, really nothing else than forwarding Slurm parameters into it. For some reason, that was not very clear for many people. And much of that can actually be automated because there are two scontrol commands that basically allow you to detect the full Slurm configuration, at least on the clusters that I've tried it on. It's like scontrol show node and scontrol show partition, and there's overlap between the information that they show, but combined, they basically show everything, including if there's extra GPUs or whatever. And I have started to work on basically one command that you can run on your cluster, and it will basically just detect Slurm configurations, set up reasonable logical providers and logical executors for those providers, and then users can immediately get started. And if they want to tweak that configuration further, they can, but at least it provides them with a starting points, or it can detect if they ask for too many cores per node or whatever, that these things are not available. And surprisingly, that those type of errors were still very common. Maybe this is related very much to my field or something, but yeah, that was an issue.